Everyone. Today we are going to talk about the Ukraine war and how we can use applied math to formulate some of the strategies. So, you might have heard by now that one of the big reasons for Russia's failure so far has been their poor logistics and the phrase amateur stock tactics, professional stock logistics. Now, logistics is a fundamentally, applied math problem. Even without the context of war, you have things like the transportation problem, shortest paths in graphs, which Google Maps uses to show you directions, etc. And if you add the layer of warfare on top, these problems get even more interesting. And that's in fact, how the field of operations research was born during the Second World War. So there are other ways that data science can be used to kind of affect the war, using game theory for the negotiating table, using computer vision to detect certain interesting situations based on satellite images, like tanks being unaccompanied by air support or infantry cover. So you can take the appropriate actions, identifying high value targets like fuel trucks, but we are going to kind of focus on the logistics angle here. So, some disclaimers. This war, my position is it should end immediately, and when we'll be solving these logistics problems, we'll be solving them often from one perspective, either the Russian or the Ukrainian. But that doesn't mean we are taking sides, because just like when you're playing chess, you need to know the best options available to your opponent as well. So solving these problems will help both sides, and they'll probably help neither because these are toy problems. So first, what does the chessboard look like? So the chessboard here is a graph with the cities, Ukrainian cities, as vertices, and the roads connecting them are the edges. The way I made this graph, if you're curious, is I just went to Google Maps, looked at the cities, the road networks, took out the details, and just connected some cities that looked important. I'm probably missing a lot of cities, villages, maybe some big cities as well. And then there are some special vertices, which are the staging areas where Russia was amassing troops before the invasion began, sometime in February of 2022. And these two of these staging areas are in Crimea, which Russia annexed in 2014, but you get the point. Now, another important aspect is that Russia, when it started the war in February, it said its objective was to topple the government and demilitarize the country. And the Ukrainian president declared that he would just stay in the capital and continue running the government from there. And so Kiev becomes very important, right? Russia can't declare victory unless it captures Kiev, at least in the initial phase. And the President Zelensky, when he was offered to get evacuated from Kiev, he famously said, "I don't need a ride, I need ammo." So the point is that Kiev is a especially important vertex on this graph, something of a king on the chessboard. Now, what are some parameters, on this graph? So these edges, which are the road networks, will have some properties. The vertices will also have some properties like the size of the city, etc. So let's look at the edges first. So we'll only think in terms of Russian tanks, right? In reality, there are various kinds of units, but they kind of move together in a combined arms formation anyway. So we can just, get rid of that complexity and think of them all as tanks. And one obvious thing is, how long does a tank take to cross an edge? Given an edge E, how long does a tank need to cross it? So we'll call that TE for an edge E. And we can think of them as weights. And one obvious thing you can do is solve a shortest path problem. So you're Russian tank, you're a Russian tank operator, you're in staging area 7, you need to get to Dnipro. What is the shortest path and how long is it going to take, on that shortest path? And this is the problem that Google Maps solves for you, when you ask for directions. But this is obviously way too simple for the Russian tanks. They have many other problems. Another thing is that they need to consider is that there's some probability that their tank won't make it past an edge E, right? So there's some probability PE, a finite probability P that the tank will actually cross the edge. And if it crosses, the average time will be TE, right? So these are two important parameters for the edges. Now, you know, what are the factors that affect TE and PE, right? One is the obviously the length of the roads. So if the road is longer, it's going to take longer, so TE is going to be larger. But it's going to affect PE as well, because the longer the road, the more chances there are for you to get ambushed, for you to run into a drone, an enemy tank. So, both of them are going to be, PE is going to be worse, TE is going to be worse if the road is long. Then how close are you to your supply depot, right? These tanks, they run on fuel, and you need fuel trucks to refill them. And maybe you have had enough fuel when you started the trip to kind of cross an edge from one city to another, but if you didn't and if you ran out, then you'd be desperately looking for the next fuel truck. And if that doesn't arrive, there's only so long you can just stay stranded in a tank in the middle of enemy territory. So at some point you're going to abandon that tank, and then that tank is never going to make it to its destination. Distance to the closest supply depot is very important. Then how much pressure the Ukrainian military is putting, that on the edge, that particular edge is a road, and the Ukrainian military could be, it could be infested with Ukrainian military, right, on both sides of the road, in the air, they could have drones, etc. So, how many resources is the Ukrainian military dedicating to that particular road? And there are many other factors as well. So now that we have the graph, what are some problems we can solve on this graph? One is a maps app for tank operators. I already alluded to this earlier. You're a tank operator at some place on the graph, staging area 7. You want to get to Dnipro. You pull up Google Maps. It tells you the shortest distance, right? And an ETA customized to your tank. But that's kind of that question is less important to you, right? How long it's going to take you on average. What's more important to you is, will I make it there at all, right? Because like I said, there's a finite chance that your tank won't even make it. So if you follow a particular path along the graph, then the total time it will take you is basically the sum of the TE values for all the edges, so T1 plus T2 up till Tn, where there were kind of n edges along this path you took. And if P1, P2, Pn up to Pn were the probabilities of crossing those edges, then the probability you'll cross the path is the probability you cross the first edge multiplied by the probability you cross the second edge, and so on, right? So those are the two aspects you need to kind of keep in mind. And as a tank operator, you'd probably want this number to be really high. You'd want this number to be as close to 1 as possible. Maybe you wouldn't care as much about this, the time it takes. You'd care more about getting there in one piece. Your leadership's opinion might differ slightly. So now let's say that actually getting the tanks in one piece is really important. Then we have a problem, because the min path algorithms, they are based on the assumption that the weights of the edges, which is the times in this case, in the first case, are going to be additive, right? If you go along a path, you can just add up the times and get the time for for the whole path. But with the probabilities, they are multiplicative, right? But that can be easily addressed by instead of the probabilities, we just consider the negative of the log of the probabilities. The log of a number between 0 and 1 is negative, so we take another negative, and that becomes a positive number that can be between 0 and infinity. right? If the PE is 1, it's 0. PE is very close to 0, it becomes infinity. And then it becomes a minimization problem, because you want these weights to be as small as possible, right? And so, with the negative log PEs, you can use algorithms like Bellman-Ford, Dijkstra's algorithm to, solve the, min, the path with the minimum sum of weights. Just like Google Maps does for times, you'll get a customized, set of directions that take these probabilities into account, and it'll tell you the best path, right? And just like Google Maps shows you an ETA, this will show you what are your chances of, actually making it in real time. And another thing is that this is going to be way more dynamic than Google Maps, right? Even Google Maps sometimes tells you, oh, I found an alternate route. Would you like to accept? And that's going to happen way more frequently in this context, because it's a battlefield, the situation is changing, and so probably these parameters get adjusted, and then the maps app shows you some alternate route which has a higher chance of you actually making it. So that's the first application. Now how can we take more high level decisions? How can we kind of actually direct the tanks? So first thing is, what are the how many tanks should you place at your various staging areas, right? So you had 7 staging areas. So how many tanks should be at should go to each of these areas, right? um, Wait, let me, yeah. So so what you can do here is, first you can say in this graph, what are some key cities I want to take. We said earlier that Kyiv is kind of a king on the chessboard, but that's not quite true, because if you really focus everything on Kyiv, Zelensky is just going to go to the Kharkiv, the next biggest city, and say, I'm running the government from there. So you really want some, you want to have some secondary objectives as well. So you really want a list of cities, that you want to take. So these are this is a good list. Kiev, Kharkiv is the next biggest. Dnipro is central. Odessa is a port city. It's going to cut off access to the sea. And so now you want to take all of these cities, and for that you want to get a certain number of tanks to each of them, right? You assume you're going to need a certain number of tanks to actually take the city. So we can think of the movement of tanks as flows on the edges of the graph, and then we can apply some of these flow algorithms. What's applicable here is kind of what's called the min cost flow problem. So let's first look at the problem very quickly. You're given a graph just like our directed graph here, and you also have some capacities for all the edges, and then you have some weights, right? So here this one is the capacity and this one is the weight, and then you have some for each vertex you have some supplies and demands, right? So this is a vertex which has a supply of 20, and this vertex is doesn't have any supply. This vertex 3 has a supply of -5. In other words, it has a demand of 5, right? And you can see that all the supplies add up to 0, right? So this is 20, and the -5 -15 add up to 0. And then how do you kind of make your items, or in our context tanks, flow from the supply vertices to the demand vertices, right? In a way that you don't exceed the capacities first of all, and the sum of weights overall is minimized, right? So in our context, we can think of the weights as the minus log PE values, and we can say that the kind of total minus log PE value depends it tells you how much damage your tanks are going to take, right? And in some cases the damage could be absolute, meaning just the ghost of your tank makes it to the destination. The actual tank is broken down somewhere in some street. But that way you can assume that all the tanks that set out actually make it, just some of them are so damaged that they're not effective at all, right? So you want to minimize the amount of damage they're taking, right? So what you can do is, you can kind of with the graph we had earlier, I kind of skipped over it last time, where I just put some dummy values for the minus log PEs, right, for each edge. So this is like an adjacency list, where staging area 1 to Chernihiv, the negative log PE value is 5, and so on. And on that graph you can those become basically the weights, right? Just like in the in this picture. So that those become the weights, these second numbers, right? And then the capacities basically tell you how much how many tanks can flow. So you can set them as infinity, or you can play with them and set them to smaller numbers if you want the algorithm to distribute the flow, right, across many edges. So by default you can set it to infinity, and then you can play with that capacity number. And and then you can kind of assign the supplies and the demands, right? So one thing you can do is you can take the number of tanks that were amassed at the 7 staging areas, and say those are the vertices with the supplies. And then you can say here are the demands, right? The demands are basically at the city. So let's say Kyiv requires 3,000 tanks, right, whereas Odessa requires 2,000 tanks, right? So we know that there were roughly 5,000 tanks to start with in the war, and let's say 3,000 of them were here, 1,000 were here, and so on. And then there are requirements, right? So for Kyiv it's the highest probably. For Kharkiv, maybe you need 1,000 tanks to get there, right, and so on. So you can set these supplies and demands on these vertices, and then you can just run the max flow, the min cost flow algorithm, which will tell you how to get the tanks from the sources to the destinations with the minimum possible damage, right? Or what you can do is you can say that I want the algorithm to also tell me how many tanks to send to the 7 staging areas, right? And the way you can do that is you can connect all the staging areas to a dummy vertex, right? I was going to show you. Let's see if I can pull this back up. Okay, never mind. So you can connect the staging areas to some dummy source vertex S, and then your you can put the number of tanks you have available at the S. So here, like this S is the source vertex, the dummy source vertex you just introduced, and you can say that the supply at this source vertex is 5,000, which is the total tanks I have. And then these new edges that you've created, you can say the capacity is infinite, and the weight is 0, right? Because there's almost no chance that the tank won't make it, because this is in friendly territory, right? And then there is the graph kind of inside of Ukraine, in the actual war zone. And so when you solve that version of the min cost flow problem, it will also tell you how many tanks to send to all of these staging areas. And once this code here, I'm going to link this blog in the description, but this code here solves that problem, and you get these different flows. These red bars are the flows. They represent the flows from the different staging areas to your target cities, right? So you can play with this code. It has good comments to tell you what's going on. Play with the parameters, have some fun, and come up with different solutions for how to direct your tanks, etc. And then from the Ukrainian perspective, one thing is, once you have a flow, you can say what is the min cut of that flow. So the min cut means, what edges should I cut to kind of disrupt this flow. And then you can kind of send your drones and your infantry with the missiles to those roads, right? And another thing you can do is, since you control the graph, you can say, how do I come up with a graph that makes it, even in the best case, makes it hardest for the Russians, right? So those are some ways this problem can help from a Ukrainian perspective. Thank you. That's all I had.